This month, we're visiting the often neglected outer solar system, taking a fresh look at Uranus, Neptune, and Pluto. We've also got news of what might be the largest comet ever discovered. Welcome to the Sky at Night.
Four, three, two, one, and liftoff.
Since the 1950s, the dream of exploring our solar system has become a reality.
The first reconnaissance flights to Jupiter in a search for basic facts about the giant gas ball.
We have sent spacecraft to Mars, Venus, Jupiter, and Saturn. But while there have been around 100 missions to the inner planets, only 2 have encountered their far-flung neighbors. Voyager 2 visited Neptune and Uranus in 1989. And more recently, New Horizons had a brief encounter with Pluto in 2015. Both missions revealed astonishing new worlds never seen before. Chris went to meet Carly Howard, whose work on the New Horizon mission produced a picture that made us see the former planet in a whole new light.
Well, Carly, I remember talking to you just after New Horizons had flown past Pluto, had sent the first photos back, which I know you worked on. Remind us what we saw in those images and what we found out since.
So the images return this amazing world, really diverse, both in its coloration, but also in its structure. The main feature was this heart-shaped region located in the middle of Pluto. It's actually on the equator, that was very white, very bland, actually. No real features in it, which is interesting in itself. And then the rest of it was sort of had a lot going on with mountains, with some mountains with a hole in, very interesting. Craters, yeah, just sort of almost like icebergs hitting the edge of this ice region. Just there was just a lot going on in this image.
Let's talk about Sputnik Planeta, that's the heart-shaped region,
yeah.
And its smoothness. Why is it smooth?
It was really intriguing, and to a planetary scientist, the first thing that draws your eye is anything that's smooth, because that shouldn't be there, right? Everything in our solar system is cratered. We have things bombarding surfaces throughout its entire history. And if there is a region without craters, that's telling you that something is eroding those craters. And we think what's happening on Sputnik Planitia is that there's this slow overturning in ice. The ices are being warmed at the bottom, they're coming up, and they're eroding. Anything that was on the surface is the cool ices that were on the surface then get pulled back down again. A little bit like a lava lamp kind of overturning. Pluto doesn't have a big gas giant next to it where it can grab some tidal energy. So whatever Pluto was formed with is what Pluto has. There isn't a magic source of energy. So that implies that the radiogenic isotopes that Pluto had upon its formation have been enough to keep Pluto warm. And so we're not really sure why that happens. Perhaps Pluto has a blanket around it that's sort of holding the heat in. And that's one way that it could have retained this heat, but it was a surprise to a lot of us.
And if we're talking about a heat source inside Pluto, that brings up the question of its interior. And people have speculated there might even be an ocean there. What's the evidence for an ocean on Pluto?
Well, there's a few different things. So the first is, of course, that we do see this active geology, and that implies there's a heat source which gives you sort of the right setup to have an ocean. Of course, if everything was frozen telling you there's probably not enough heat to keep an ocean alive. And the second thing is just trying to understand what's going on Pluto, with Pluto's geology. So we see this heart-shaped region, we see that it's at the equator, but for that to just form there would be a little bit weird. So if there was an ocean between the rocky core and the outer ice shell, it would enable that ice shell to just move a little bit and maybe relocate that heart-shaped region to the equator where it's a little bit more stable.
We've of course got other places we could explore. One of the Pluto-like places maybe is Triton, Neptune's moon. What do we know about Triton?
So when Voyager 2 flew past Neptune in 1989, I think it returned about 50 images of its large moon Triton. And Triton is a really weird world. It's a bit of a pet hobby of mine. I love Triton. On the one hand, it's a plume world. We know that it has active plumes going off. When Voyager 2 flew by, it saw these huge columns of material coming up and being pulled into trails across Triton's surface. It was the first plumes we've ever seen in the outer solar system. We don't really know what they're made of because Voyager 2 wasn't able to determine the composition as it flew by. It didn't have the right instrumentation for that. So if we went back one day, we'd be able to, that's something we would definitely want to look at. But the idea is it probably does have maybe more of an exotic ice feel, so a bit more Pluto-like, so maybe some, again, carbon monoxide, some nitrogen, maybe some water too. It depends on what the plumes are made of, or like where they come from. So if the plumes are connected to the ocean, it's probably a bit more ocean material, more water, a bit more like brine. If they're not, if they're just from the very surface, then maybe a little bit more exotic ice, carbon monoxide, carbon dioxide, nitrogen, methane,
You've really got to go back to these places to explore them properly. If you got to go back to Pluto or send a mission to Triton, what are the big things you'd hope to discover?
The fundamental paradigm shift would be to fly through the plumes, to really determine whether life exists in these worlds and whether we can sample that without damaging the pristine surface. And plumes are the prime way to do it. And just look for life. Does life exist in these places? I mean, what a fundamental change that would be in our understanding of our place in the world.
And what about Pluto? What would a New Horizons get you?
An in situ, like an orbiter New Horizons. The big thing would be, does it have an ocean? Because if it has an ocean, then again, it feeds into this idea of where could life exist. All those pinpricks of light that are distant from these other suns that we see could host life too. If Pluto has an ocean, why not any of the literally millions of worlds? And what does that mean for life? I mean, that would just be mind-blowing and huge.
Somebody who shares Carly's conviction that the outer solar system is due a revisit is planetary atmospheres expert Lee Fletcher.
Good to see you, Lee.
You too, Maggie. Welcome to Leicester.
Maggie went to meet him to discuss other potential targets for a mission to the forgotten solar system.
So, Lee, Voyager flew past the ice giants. We got lots of information. So what did we learn, and what have we learned since?
Yeah, you have to cast your mind back to the early 80s. Uranus and Neptune were mere points of light still at that moment. And the Voyager spacecraft barrels on through those two planetary systems in 1986 and 1989 and takes incredible observations during that period, and then that's it. Then you have, fast forward 30 years to the present day, and that Voyager dataset taken with 1970s technology, it's still the best dataset we have to this day to understand those worlds. I'm told, actually, that Voyager scientists, when they first saw these images of Uranus, were actually disappointed. They were so used to seeing gorgeous Jupiter, they were used to seeing all the structures on Saturn, then they finally see Uranus, and it looks like that. And I think they were disappointed by what they saw. But the problem was, they just weren't looking at it in quite the right way. If you tune your filters with near-infrared observations, you can actually peer down through the overlying hazes and start to see all the tremendous structure that's present within the atmosphere of Uranus. And it starts looking a bit more Jupiter-like, with storms erupting, with bands and belts and zones. Absolutely, what we would love to be able to do with these systems is go into orbit around Uranus and/or Neptune.
So what can we learn
learn? So let's say your dream comes true. We have a system, it goes in orbit. And also, there's a question of which one. Do you think we can go into orbit around both? Or?
Well, that's an excellent question. Uranus and Neptune, or Uranus or Neptune, has been a debate that's been raging in the planetary community for many years, because there are different reasons why you'd want to go to each one, and actually comparing them is where the real magic will happen. By comparing these two worlds that may have had similar origins back in the early days of the solar system, but have now diverged and evolved along very different tracks. Now, what we would like to really understand about Uranus and Neptune is that they're like missing links in our solar system. They're the last class of planets that is yet to be explored by a robotic spacecraft, if you ignore the wonderful flyby from Voyager.
Yes.
Now, that particular size of planet, roughly 4 Earth radii across, it seems to be the most common outcome of the entire planet formation process. When we look at this huge census of extrasolar planets, some 4,000 and counting, we see that worlds just slightly smaller than Neptune are actually commonplace in that census. So here in our backyard, in our solar system, we have 2 examples of the most common outcome of the planet formation process, and yet we know very little about them. We don't even know that they're made of ice. We call them ice giants.
Okay, that's embarrassing.
Well, it is a bit of a hidden mystery in planetary science. We know that a lot of the stuff that would have made Uranus and Neptune in the first place was a blend of rock and ice. And we know that these formed beyond the snow line, which is where water would be condensing. So water would be a great first guess as to what the main constituent would be. But they could be 50-50 rock and ice. They could be rock giants rather than ice giants.
So we're not talking about a flyby. You want to go sort of into orbit around these planets, study the moons, look at the atmosphere, sort of do it over a long period of time.
Yeah, a flyby is not enough. A flyby will be over so quickly. You'll get some fantastic new images and you might get some new insights, but you won't have that step change, that paradigm shift in our understanding of this class of planets, this class of objects, unless you go into orbit around them for a long period of time.
Yeah, so you're thinking of sort of a Cassini-like mission.
Absolutely.
Going out there.
Take all the instruments you need with you that could enable discovery-level science. You don't just build the instruments that you know will address a certain question. You build instruments to be flexible enough that they could potentially discover something new that you haven't even dreamt about yet. Because I guarantee you, Uranus and Neptune are the destinations in our solar system where those sorts of fundamental new discoveries could be made. But it's extremely hard getting a mission out.
So why hasn't it happened?
So there is a lot of politics that go into big missions like this. We're not just trying to sell to scientists like us, we're trying to sell and convince people who may never have thought of the outer solar system before us to why this is such an important thing to try to do. In particular, people who will fund us and politicians who will make those final decisions. Now, in Europe and over in the United States at the moment, there are these, they call them decadal surveys taking place, where scientists from across the globe come together to try to set the strategy for planetary exploration for the next decade.
Yeah.
Now, we have said time and time again that the ice giants should be top of that list. They should be the places that we should go. And in the next 6 months, sometime in 2022, those panels, those surveys will report back and tell us what's at the top of the list. If it's Uranus and Neptune, then we may finally see the opportunity within our lifetimes to have an orbital mission around either Uranus or Neptune, dropping a probe into the atmosphere for the very first time, and really bringing our understanding of what an ice giant system is, what it's made of, how it connects to exoplanets, whether life could potentially exist in subsurface hidden oceans on the satellites, bringing it up to a level of maturity that we can only see now for Jupiter and Saturn. So those forgotten worlds in the frozen outer reaches of our solar system, we might now be on the cusp of starting an ambitious mission to go explore them. And I, for one, am excited about it.
Well, Lee, you've definitely sold it to me, and hopefully in 6 months you'll get the go-ahead and we can come back and design the mission.
That would be fabulous.
It would be an amazing thing to do.
It would be the most incredible paradigm-shifting mission that we're ever going to get in the next 20 years of space exploration. And Uranus and Neptune are just waiting out there to reveal their secrets to us.
You can see all the planets of the solar system from here on Earth, even the outer ones. So here's Pete to tell us where to point our telescopes and to tell us what we might see of Uranus and Neptune in the October sky.
The ice giants Uranus and Neptune are very distant worlds. And despite their considerable size, even a large amateur telescope, such as this one here, will struggle to see any detail on them. So what hope has a small telescope got of seeing anything of our distant solar system neighbours? Well, let's find out. Okay, let's start with Neptune. Now, Neptune is quite faint. You need at least a pair of binoculars to see it, and when you do find it, it looks just like a faint star. It's currently located in the constellation of Aquarius, and the easiest way to get to the right general location for it is to identify that familiar pattern of the autumn night sky, which is the Great Square of Pegasus, and that's quite high up, late evening at this time of year. Once you've identified the Great Square, use the western edge, that's the right-hand edge of the square, and extend it down by about 1.8 times. Now that will bring you to a pair of faint stars, Lambda and Phi Aquarii. If you draw a line from Lambda through Phi and extend it on for about 0.6 times again, that'll bring you into the right general location for Neptune. Now, when I look at Neptune through the eyepiece of this telescope, I can see an object which has got a sort of grey, bluish hue to it. But to be honest, even with the highest power here, I'm struggling to see anything more than a star-like point. What you really need is a telescope which is 6 inches to 8 inches in diameter, and again to use a high power over, say, 200 times magnification. And then you should be able to see Neptune as a disk. Uranus is easier to find than Neptune because it's brighter. In fact, Uranus is so bright it's on the threshold of naked eye visibility, but you do need a really good dark sky sight in order to be able to see it without any optical aid. Binoculars are probably a better way to pick it up. Even then, it'll just look like a tiny star in your field of view. Through my telescope, it looks like, again, like a sort of star at low power, but it does have a very distinctive greenish hue to it. And that comes out better than Neptune's colour because Uranus is brighter. If I ramp up the power to about 200 times, I can just about make out the planet's disk, but it is quite small, even so. So how do you find Uranus? Well, we can use 2 stars of the autumn sky, Hammel and Menkar. Hammel's the brightest star in Aries, and Menkar is the primary star of Cetus, the whale. If you draw a line between those 2 stars, find the midpoint and look slightly to the east of that position, that's where Uranus is currently located. If you do get clear, dark skies, go out and see if you can find these 2 planets. Even if you're just using a pair of binoculars, it's still pretty cool to say that you've seen the most distant planets in our solar system.
Of course, planets aren't the only thing that orbit our sun. Comets live largely outside the furthest reaches of the planetary orbits, only coming in to visit us now and again.
Some comets are regular visitors, others appear just once, but all have the potential to tell us more about how we got here. So when one appears, it's always an exciting moment. Chris talked to astronomer Michelle Bannister in New Zealand about the exciting and enormous new kid on the comet block.
Morning, Michelle. How are you?
Bon Marie, good evening.
Michelle, it's wonderful to talk to you. I hear there's a new comet, and you're the person to tell us about it. So what's been discovered?
This is pretty exciting. It's the largest comet to be found in the Survey telescope era. So that's pretty amazing. Comets are normally on the order of maybe a kilometre to a few kilometres across. This one's big. This is on the 150-kilometre range. So not as big as the UK, but pretty sizable.
Sorry, how was it discovered?
It was found by a graduate student. So Pedro Bernardinelli and his supervisor, Gary Bernstein, were using a computer and software that they'd written to scour through images that had been acquired by a big telescope in Chile for a thing called the Dark Energy Survey. But they're using this data for a completely different purpose, to see what's moving across the sky that's in the outer solar system. And so this discovery was a complete bonus. So this is pretty amazing. This got the comet world really excited, I would say. Telescopes all around the world immediately started looking to see this little world's coming from the very edge of the solar system, from tens of thousands of times further from the sun than we are here on Earth. But it's been found when it's 20 times further from the sun than we are at the moment. So what's it doing? It's been in the deep freeze. Is it active? So we went to have a look.
So professional observatories have already been looking at this thing, following up on the discovery. What do we know about it so far?
Well, it's so far from the sun still. It's nearly 20 times further from the sun than we are here on Earth. It's inbound. It's coming into that closest approach outside the orbit of Saturn, but it takes a while for it to travel that far. So one of the things that everyone was excited to find out was, when is it going to become an active comet? And so we have a program on that called LOOK, which is basically, it's an acronym, but let's go and look at things that might be active. And so we triggered the LOOK program to go and see. And it happened, we're a collaboration all around the world, but it happened that it was about 4:30 in the afternoon my time when the first images landed. And so I went, okay, I'll open them up and have a look. And there were 4 images. And I opened the first one, and there was a satellite trail right across it. And then I opened the second one, and there was a satellite trail right next to it. And so I was going, okay, how are we going to be able to tell? And then the third and fourth images we could use. They didn't have a satellite trail on top of the target. And so then you could see it was fuzzy. It was this little fuzzy dot of light. It wasn't point-like like the stars. And that meant it had become really active now, enough that you'd really think of it as a comet. So as it comes in, telescopes all around the world and off the world are going to have a front row seat for the event of the decade of having one of these really incredibly large comets, as comets go, come and go through that perihelion, that closest approach to the sun. Now, while it's still going to stay outside Saturn, we'll be able to see it for all the years coming up through 2031, going back out again. So yeah, it's going to be a pretty wild show, I think.
So what will this comet tell us?
This is a comparatively large world as comets go, you know, a really big one to find. And so what's it going to tell us about how an ice block that's been in the deep freeze potentially ever since it formed, how's it going to change and evolve as it's heated for the very first time? That's what we're going to be able to find out from this, is how does a comet like that, it's such a large world, how will it become active? What chemistry will come off its surface? What kind of dust will float up and away? So we'll be watching to see how it changes and what that looks like.
And of course, these are all clues to how the solar system's early history played out, because these are the building blocks from which some of our solar system was assembled.
Yeah, a comet is a time capsule. It's something from the earliest stages of formation of the small worlds that came together to become planets. So this is one of the ones that didn't become a planet. So this can tell us about what these building blocks are like.
And will it ever come back to the inner solar system?
Not while anyone who's alive today will get to see it.
Well, we'll make the most of this opportunity, and keep an eye on it for us, Michelle, and we'll talk to you soon.
We'll try. Thanks, Chris.
While as yet there are no missions planned to the outermost planets, comets have fared better. In 2019, we reported on the audacious Comet Interceptor project, submitted to ESA by Geraint Jones and his team.
Just received an email from ESA confirming that Comet Interceptor has been recommended for further study. So, yeah, quite a relief.
Maggie ventured into the Surrey Hills to UCL's Mullard Space Science Laboratory to find out how Geraint's winning project is progressing.
Hello, Geraint. It's lovely to see you again.
Great to see you.
Especially on a sunny day.
It's wonderful, isn't it? Yeah.
Now, last time I saw you, you just had the go-ahead for the project. So how's it all going?
Yeah, really well, thanks. The next big step is in the middle of next year, 2022, when we hope that the European Space Agency will adopt the mission. So that's basically the ESA member states rubber stamping this proposed mission. And, yeah.
Yes, so you get sort of confirmation, you get go, but that's sort of the next stage in a process, which you're sort of, so you get verification, you get confirmation, and then there's a next stage where you say, okay, start cutting metal or whatever.
Exactly, yeah. So despite the many complications of COVID, we're pretty much still on target, and yeah, June next year we'll get the go-ahead.
Ah, fantastic. So tell me, remind us about how this configuration works, because there's actually 3 spacecraft, or spacecraft and 2 probes. How does that work?
Yeah, so there's a main spacecraft, which we're calling Spacecraft A. Very imaginative. I'm sure we'll come up with a better name nearer the time. And then probe B1, which is being provided by our colleagues in Japan, and probe B2, which is a European probe.
Spacecraft A will chase down the comet and drop the probes B1 and B2 into its tail, and will store the data they beam back.
For most of the mission, the 3 elements will be together, and we'll be sitting at L2, which is this location in space where it's quite stable, and yeah, the 3 spacecraft can stay together there while we hunt for our target.
Yeah. Now, hunting for the target, what sort of target are you looking for?
Well, we want to go to a long period comet, so that's one that takes a very, well, as the name suggests, ideally millions of years to orbit once around the sun, or if we're really lucky, then an interstellar object as well, so a comet that just happens to be passing through the inner solar system at the right time. We'd have to be really lucky to get one of those, but
they come along.
Yes, they do. 2 in the past few years, so we know they are out there. Yeah, but the primary target is a long period comet. And ideally one that's called dynamically new, which means it's coming in towards the sun for the first time since it was formed billions of years ago.
Now, it sounds strange waiting at Lagrange point 2, because sort of, it sounds a little hazardous. What if a comet doesn't come along? It's sort of, how is it, have you got to being there?
Well, it's true that a few members of our team also pointed out when we first proposed it that ESA will never go for a mission to where we don't have a target to go to.
Yes.
But we've made our case, which I believe is very robust. And the thing that's really changed the game is survey telescopes. So we have several observatories now that don't look at a particular target every night, but basically map the sky, looking for changes. It serves all areas of astronomy and astrophysics, looking at variable stars and also the large-scale structure of the universe. But we're looking for things that are moving, which weren't previously known about, and many of these are comets. And one observatory that's expected to really change the game is the Vera Rubin Observatory. So it was formerly known as LSST, and from its site in Chile, it's going to be mapping the sky every few nights. So it's a huge telescope, 8.5 meters diameter. And although it's not going to find more comets than the current rate of comet discovery, it is going to find them much further away because it's so sensitive. It can find really faint objects when they're still really far away from the sun, and that gives us a lot more advanced notice of where comets are going to be in the future. So hopefully one of our targets is going to be amongst them. And we're really looking forward to launch in 2029 and the data eventually streaming back.
Perfect. I look forward to that too.
75 years ago this month, the very first images of Earth from space were recorded by a movie camera attached to a captured V2 rocket sent 65 miles into the sky above New Mexico. It's astonishing to think how far we've come since then, from capturing images of our own planet to sending missions to the distant outer solar system.
Next time, we'll be looking at some of the amazing telescopes that have helped shape our understanding of the night sky, in anticipation of the launch of NASA's James Webb Space Telescope. Until then, good night.